All right, guys. So a handful of students were asking for some review help on simplifying radicals. So um, let's get down to that. So simplifying radicals. Understand the parts of that radical question. We have the radical symbol, which on its own does not mean square root. The index is what tells us what root we're looking for. So that index is really important. And then, of course, we have the radicand, which is whatever is underneath that radical symbol. Now, whenever that index is missing, and you can see that right in the bottom, um, it indicates that there's a 2 there for a square root. Okay, now we are going to be working with square roots, but some of the techniques that I'll show you will work whether you're looking for a third root, fifth root, whatever, and like in Algebra 2. Um, But whenever that index is not shown, it is automatically an invisible 2, working with square roots. So there are some rules for simplifying square roots, and you can read these. No perfect squares can remain, meaning we have to simplify it as far as possible. No fractions can stay under that radical symbol. And the third one is no radicals can remain in the denominator. So what we mean here, um, we cannot have a fraction inside the radicand. This is not allowed. And we also cannot have a radical in the denominator. So a radical in the numerator, that's okay. But a radical in the denominator is not allowed. Then that requires a process called rationalizing the denominator. And we'll get to that in just a little bit. We'll start off with just simplifying a radical, and then we'll get to working with multiplying and, in this last case, dividing by a radical, because that radical is not allowed in the bottom of a fraction. Remember, the fraction bar means divide, and we're not allowed to have a radical there. So we'll get to that in a few minutes. All right. So we're working with square roots, and a square root, the square root symbol is effectively it's asking us what number was squared to get here. So think about this, in some simple examples. If we look at the square root of 4, it's asking us what number was squared, meaning multiplied by itself, to get a 4. And we know the answer is 2 because 2 squared is 4. If we're asked to work with the square root of 25, well, that means a 5 was squared because we know 5 squared is 25. So these are called perfect squares, where when we take the square root, we get a number. The square root goes away. Again, it is asking us what number was squared. A 5 was squared to get the 25. So we're doing the opposite of squaring, square rooting. And that's really important. Now, most of the time, when we work with our radicals, we're not going to have a perfect square, like square root of 25 or square root of 36. It will happen, but usually not. So sometimes we're going to have this situation, and here's an example, the square root of 18. Well, there's no number we can square that will perfectly give us an 18. When we are simplifying radicals, we will never put them into the calculator and get a decimal. That's not allowed. We have to work in radical form, meaning with the square root symbols. So what we want to do is we want to break down that 18 and think about, well, how did we get 18? Well, I know that 18 is made up of a 9 times 2, right? And we all know that. 18 equals 9 times 2. And 9 is a perfect square. So if we leave them under the radical symbol, we have the square root of 18 equals the square root of 9 times the square root of 2. And it's really nice because the 9 is a perfect square. 3 times 3. So again, if we think about it as the radical symbol is asking us, what was squared to get 9? And the answer is a 3 was squared to make the 9. That square root 2 just gets pulled down. So we end up with 3 square root 2. So the square root of 18, when we simplify it, is 3 square root 2. Now, this approach requires us to identify the greatest perfect square factor, meaning 9 is a perfect square, and it is the biggest perfect square that fits into the number 18 evenly. In fact, it fits twice. So that's a perfect square approach. There's more than one approach to things, but that is one way of doing it. And again, we are factoring it. We're just identifying the biggest perfect square that is a factor. So let's look at a few more numbers here. For the square root of 27, the biggest perfect square that goes into it is a 9. 9 is a perfect square. So 27 is made up of 9 times 3. It's still all under the radical sign, or the house, whatever. We should call it radical symbol, but I understand. And since the 9 is a perfect square, we can effectively, sorry about that. The 9 is a perfect square, so it will come out as a 3, and the square root of 3 just stays the way it is. When we look at a 48, well, a 48 can be factored a few different ways, right? I mean, 12 goes into 48, 24 goes into 48, but none of those are perfect squares. The biggest perfect square factor is a 16. So we're going to break it into a 16 and a 3. The square root of 16 is 4. So again, we're looking at this as the square root symbol is asking me what was squared to get here. So a 4 was squared. That's why you only see 1 4 on the outside. That square root 3 just stays the way it is. So this is the greatest perfect square factor approach. We could also use the approach of doing a factor tree. Now again, it's just a different approach. One is not better or worse. One is not easier or more challenging. It is just a slightly different approach. So here we're looking at the same examples. So in 18, and I can create a factor tree however I want. It does not matter. And I broke it into a 2 and a 9. And that's fine. The 9 gets broken into a 3 and a 3. So I'm taking it all the way into my prime factors. And now, since the index was a 2, right? And this is, I want you to look at this paragraph right here. Since the index was a 2, I'm looking for 2 of the same number, or pairs. Each pair will go as one number on the outside. So since we have a pair of 3s, I get a 3 on the outside. The 2 is going to stay underneath the radical symbol. And we get the same 3 square root 2 that we did a few minutes ago. Now, you can do your factor tree however you want. For example, let's come over here on the right, 18. Well, I can split that into a 3 times 6. And then the 6 is broken into a 3 times 2. And as you can see, there's my pair, 2 of the same number. The pair goes out as 1. The leftover stays home. So I use the analogy of the buddy system. When you were a little kid and you wanted to go out to play, you had to go outside and stay together with your friend or your sibling, whatever it might be. You two stay together. When I look outside, I better see you guys together. Well, that's what we're doing. We're taking those 2 3s and we're putting them outside, but we're putting them together as just one number. Anybody else has to stay home. And that's how we can do it through a factor tree. So again, let's look at a few more examples done this way. It's the same examples, just done through a different method. So we factored the 27 into 3, 3, 3. A pair goes out as one number. The leftover stays home. In the 48, again, I broke it down into a factor tree. I did 2 and 24. You didn't have to start there. You could have started with 4 and 12. But I did my factor tree, and I found all my factors. So my factors of 48 are 2, 2, 2, 2, and 3. And then you can see each pair goes out as one number, and the leftover stays home. Since I have two numbers on the outside, remember these are factors, so I multiplied them back together, and I got a 4. If I had two numbers left over on the inside, I would multiply them back together, and that answer would stay inside or under the radical sign. And that's how we're going to do it. So we have two approaches. You can read this slide on your own. There are definitely advantages in each method. And we'll add one more piece to it. If there's a number in front of that radical. So for example, 2 times the square root of 45. Well, the square root of 45 we already did. You can rewind a little bit. The square root of 45 is 3 square root 5. So what I'm going to do is I'm going to ignore the 2 for a minute. And I'm just going to do the square root of 45. And we got 3 square root 5. Now, as you can see, there's a 2 on the outside and a 3 on the outside. So we multiplied them back together to get a 6. And we did that in the second example also. We ignored the negative 8 for just a minute and simplified the square root of 54. So the square root of 54, and you can break this down however you want. That's a 9 times a 6, which is 3 times 3, and the 6 is 3 times 2. That gives me 3 on the outside, and on the inside, the 3 and the 2 have to stay. So I'm going to multiply them back together, and that's how I'm getting the 3 square root 6. Now I'm going to take the two numbers that are on the outside, the negative 8 and the 3, and I'm going to multiply them back together for a negative 24. Okay. So let's take a look at just a couple. We're not going to do all of these. Okay. So for example, square root of 12. So square root of 12. That's a 2 and a 6, which is a 2 and a 3. Since I have a pair of 2's, I'm going to get a 2 on the outside, and the 3 stays home. And that's how we're going to do it. Let's do number 4. I'm just going to move the page up a little bit. I'm going to ignore the 3 for just a minute. And I'm going to break down the 108. So that's 2 and 54, which is 2 and 27, which is 3 times 9, and the 9 is 3 times 3. And now I'm going to look for my pairs. I have a pair of 2's, so that's on the outside. I have a pair of 3's, again on the outside. And then I have a leftover 3, so that stays home. Multiply the numbers on the outside. So 6 square root 3. Now remember, that is just the square root of 108. Now I have to bring the 3 down from the original problem. And since I have a 3 and a 6 on the outside, now I'm going to multiply those together for 18 square root 3, and that is the final answer. So you can go ahead and try a few others. If there's a question, you can certainly reach out to me.